Welcome to Math 3A, Linear Algebra. This section 1.1 and section 1.2, are the most important in the whole course in that we'll be using these techniques that we learn in these two sections for the rest of the semester. All right, so we're going to start with just a list of definitions. First definition is a linear equation. An equation is linear if it's linear in the given variables, which in this case are x1 through xn. That means that the exponent of each variable is 1, and the only thing you can do to each variable is multiply it by a constant and then add it to another variable. So for example, this first equation here is linear. The next equation is not good in terms of linear. You cannot multiply one variable times another. Bad. Last equation, not linear because you cannot take the square root of a variable. Each exponent has to be 1. Square root has exponent 1/2. Bad. A linear system is a collection of linear equations. What makes a solution to a linear system is that it satisfies all the equations in the system. So for example, 3, -1 is a solution of this system because if I put it in the top equation, 3, -1, 3 minus 1 is 2, yes, and then 3 plus 1 is 4, yes. 2, 0 is not a solution. 2, 0 satisfies the top equation, 2 plus 0 is 2, but 2 minus 0 is not 4. So it doesn't satisfy all the equations, so it's not a solution of the system. Equivalent systems are ones that share the same solution set. So they're not equal in that, here's an example here. This is going to be a yes, the answer to this question. These are equivalent systems, and we're going to show that. This system looks different than this one, right? On the face of it, it looks different, but they have the same solution set. So how can I determine that? Well, let's do the easy one first. If x2 is 0, then the top equation would read 4x1 equals 8. So x1 would have to be 2. So the solution set to this second system is squiggly brackets, the single ordered pair, 2, 0. There's one solution. All right, now let's go over to this system. One thing you can do when you're solving a system of linear equations is add two equations together. So this gives me 2x1. This is called the elimination method in algebra. When you take like basic algebra class, you learn how to solve a system by eliminating one of the variables. So we get 2x1 equals 4. So x1 is 2. And then we go back and we plug that into either one of these two equations. If I'll go to the top one, if x1 is 2, then x2 is 0. So this has the same solution set. x2 is 0, x1 is 2. All right, so linear algebra is all about going from one system to another without changing the solution set. So if I had to solve one of these two systems, the one I would pick is the second one because it looks easier, right? So we want to be able to do things to systems to make them look easier. Here are the 3 things we can do. If you have a system, you can take any equation in that system and multiply by a non-zero number. The notation for that is squiggly means equivalent. So this system is equivalent to that one. And then over the squiggly, I wrote what I did. I took twice the first row or equation, 2 row 1. You'll see why I use the row notation later, but twice row 1. So what I did was I cleared fractions. That's not going to change the solution set. Another thing you can do is if you don't like the order of the equations, you can switch them. So I've got 2 equations here. The only thing I did to get to this system is flip the 2 equations. So the notation for that is I took row 1 and I interchanged it with row 2, and I have an equivalent system. And then the third one is the most useful. You can take any single row or equation and replace it with the sum of one equation and a multiple of another. In this case, what I did is I added these 2 equations together. x1 minus x1 is 0. So I get x2 equals 2. And then I replaced this system. I left the top equation alone and replaced the second equation with the sum of the first equation and the second equation, which is x2 equals 2. That's called row replacement. We're going to talk more about these operations in another page, so don't panic yet. That can always come later. Let's take a look at the geometry of solution sets. If you have a linear system, there are 3 explicit options, but 2 of them go under the same category. So a linear system either has no solution, in which case it's called inconsistent, or it's consistent. And if it's consistent, there's only one of 2 options. It has exactly one solution, or it has infinitely many. You cannot have exactly 2 solutions or exactly 3. And I'll show you why geometrically right now with these examples. So here we have 2 lines. Okay, now a solution has to satisfy both equations. That means if x1, x2 is a solution, it has to lie on both lines. That would be the intersection of both lines. Okay, and 2 non-parallel lines are going to intersect in one place. So in this case, my solution set is the single ordered pair. This is a squiggly bracket, 3, 2. And how many solutions is that? That's 1. So 1 solution. Okay, so 2 equations, 2 unknowns. Geometrically, what you're looking at is 2 lines. The 2 lines can either cross in one place. They can never cross. That's what I have here. So the solution set is the empty set because there are no solutions. Never put the empty set in squiggly brackets, okay? It's its own set, so just write the 0 with a cross through it. This is why it drives me crazy when students write their zeros with a cross through them, because in math, that symbol's taken. It's the empty set. So solution set is the empty set. How many solutions is that? That's 0 solutions, because the empty set is empty, all right? And then the last case, you've got 2 lines, but one literally lays on top of the other. So if I write this system as an equivalent system, so add both equations together, I get 0 equals 0. So I can replace this system with, leave the top equation alone, and then the second equation is 0 equals 0. Well, that adds nothing. That's no information. Yeah, 0 is always equal to 0. Big deal. So really, the solution set is described by the fact that negative x1 plus x2 has to be 2. So in this case, the solution set isn't so easy to write down. Solution set is the set of all, this is called set builder notation, squiggly, set of all x1, x2, such that negative x1 plus x2 equals 2. Okay, so you read that, the set of all x1, x2, that straight bar means such that, but it only means such that within set builder notation. If you just write straight bar, I'm having lunch today, straight bar, whatever, no one's going to know what you're talking about. So the straight bar only goes within set builder notation. So that's the solution set. How many solutions is that? That's infinitely many, because any point on this line is a solution. So these were 2D cases, and I think this is the best to illustrate the theorem that you can have no solution, exactly one, or infinitely many. But that theorem works for any number of equations in any number of variables. So in 3D, we're looking, each equation is going to define a plane, not a line. And so let's see how many solutions we have in each case. If I've got 3 planes intersecting in one point, I'm going to have 1 solution. Here I've got 3 planes, and they're meant to be all lying on top of one another. So it's hard to see, but 3 planes that are coplanar. So I've got infinitely many solutions. The next one, there's no way I can be on this top plane and this bottom plane and this purple plane at the same time, because the top and the bottom never intersect. So this guy has 0 solutions. And this last one, I've got 2 planes that lie on top of each other and then another plane that intersects at an oblique angle. So any point on this line would be a solution because it would lie on all 3 planes. So this would also give us infinitely many. Okay, so let's talk about the matrix of a linear system. There are 2, the coefficient matrix and the augmented matrix. First of all, just a little bit of notation. If you have an M by N matrix, then that means there are M rows. The first number is the number of rows and N is the number of columns. And so if you think about a linear system, all the information is encoded in the coefficients and in the answer column. So the A's and the B's. If you just want to look at the coefficients, and there are many cases where you really don't care about the answer column, then what you're going to get is an M by N matrix. You're going to have M rows and N columns. And for a matrix, you either have to put it in parentheses or brackets, You can't use squigglies, those are taken, and you can't use straight bars, that's taken for determinant. So there's only two proper notations for a matrix. And the worst of all is just to leave it off. So if I see in your work 3, 2, 1, 7, 6, 4, 1, 2, 3, with nothing around it, I'm going to be pretty upset. So that's really bad. Okay, so that's the coefficient matrix. If you want to include the answer column, that's called the augmented matrix. This is going to still have m rows, but it's going to have n plus 1 columns, where n is the number of variables. Oftentimes when I'm doing problems on the board, I like to put a column of dots, between my coefficient matrix and my answer column, just to indicate that this is an augmented matrix that I'm looking at. Your book doesn't do that, and it's totally optional. So let's look at an example. Write down the augmented matrix of this system. Okay, there's 3 variables, 3 equations, so this is going to be 3 rows and 4 columns. So here we go. The coefficients of the top equation are 1, -2, 1, and then 0. And this last column is my answer column. Second equation, the coefficients are 0, 2, -8, and 8. And the last one is -4, 5, 9, and -9. Okay, next one, write down the linear system that has the augmented matrix below. So I'm told that it's augmented, so I know that 3, 8 is my answer column. So this reads x1, 1 times x1, plus 0x3, so I'm just going to leave, x2, 0x2 equals 3. I'm not going to write plus 0x2 because it's kind of clunky, so I'll just write x1 equals 3, and the second line corresponds to x2 equals 8. Well, if x1 is 3 and x2 is 8, then the solution is 3, 8. You might say, well, why are you writing 3, 8 without the squiggly brackets? Because on the previous page, you wrote squiggly brackets around the solution. So the answer to that question that you didn't ask, but I asked for you, is if I ask for a solution set, then I want the set of all solutions. If there's only one solution, I'll put it in squiggly brackets. If I just ask for the solution, I'm not asking for it in set form, so you can just list it. Hopefully that makes sense. Don't worry, not very many of our systems will have only one solution, so it will be very uncommon that you'll have to just write 3, 8. Usually there'll be infinitely many solutions or more interesting things. All right, and then C, write down the linear system that has the augmented matrix below. What is the solution to the system? All right, so 2x1 minus 3x2 plus 2x3 equals 1. That's the top line. Second line is x2 minus 4x3 equals 8. And the last line, 0x1 plus 0x2 plus 0x3, well, that's 0 equals 5. So the solution to that system, remember, a solution is in this case, it would be an ordered triplet, x1, x2, x3, that satisfies all 3 equations. Well, there's no x1, x2, x3 that will satisfy 0 equals 5. So the solution is the empty set. There are no solutions. Okay, some matrices are easier to see the solution from than others. And so I'm classifying those as good, better, best. And in the next section, we'll call those echelon form and reduced echelon form. So we'll have names for them. But for now, I'm just going to call them good, better, best. Good is all your leading entries, your non-zero, the first non-zero entry of each row, form a triangular pattern, meaning going from top to bottom, they move from left to right. So we have zeros underneath. That's good. So here's an example. This is good. It's better if each leading entry is 1. So here we have a better. So each leading entry is 1, and below each leading entry is all zeros. Best is each leading entry is 1, below each leading entry is zeros, and above each leading entry is zeros. That's best because when you look at best, like the solution to this system, the system that corresponds to this augmented matrix, I can read it right off the matrix. This reads x1 is 7, x2 is 8, x3 is 3. So how do we get from good to better to best? We do elementary row operations. So these are the 3 things I mentioned on the first page that you're allowed to do to a linear system. These are reversible operations. You can always undo what you did. So the first one's called row replacement. You add a multiple of one row to another, and that the notation for that is take row j and replace it with row j plus some multiple of row I. Swap two rows, just ri double arrow rj, or multiply any row by a non-zero constant. And two matrices are called row equivalent if you can go from one to the other by doing these elementary row operations. And these elementary row operations will not change the solution set. So I'm going to do an example here, and there's a longer example I want you to read at the end. And then there's a really good example in section 1.2 that I want you to read before you watch the 1.2 video. And that would be example 3. Read that and read it carefully. It's kind of long, but you'll make it. Okay, so let's solve this system by doing elementary row operations on the augmented matrix. So we'll start with the augmented matrix. 1, 5, 7, -2, -7, -5. That's augmented. Again, those dots are optional. So I've got a leading entry up here. I want zeros below it. So what I'm going to do is I'm going to replace row 2 with twice row 1 plus row 2. So row 1 stays the same, 1, 5, 7. But row 2 gets replaced with twice row 1 plus row 2, because that will give me a 0 here. So just multiply these top numbers by 2 and add. So 2 times 5 is 10. 10 take away 7 is 3. 2 times 7 is 14. 14 take away 5 is 9. So now I'm in good form. So now let's get to better. Let's take 1/3 of row 2 so that this 3 turns into a 1. 1/3 row 2. So row 1 stays alone. So this is a 1 and that's a 3. So now we're in better form. So to get best, I need a 0 up here. So I need to kill that 5. So I'm going to replace row 1 with -5 row 2 plus row 1. So that will leave row 2 alone. And then I multiply row 2 by -1 and add it above. So this 1 won't change. And then 5 take away 5 is 0. And 7 take away 15 is -8. Whoops. I said 0, but I wrote 5. Okay, so this is best. And now I can read the solution right off. If this corresponds to linear system, x1 equals -8 and x2 is 3. So the solution is the ordered pair -8, 3. Or I could write the solution set. Solution set is the set consisting of this one solution. Either one's fine. Okay. So when you're looking at augmented matrices, you want to use this key fact, and it's super important. If the augmented matrix of a linear system has any row that's all zeros and then a non-zero number in the answer column, you have an inconsistent system because that row reads 0 equals b. If b is non-zero, there's no set of variables that will satisfy that equation. So let's look at a couple of examples. A linear system has the augmented matrix below. Write down the corresponding linear system. What is the solution set? So this first guy reads, so remember, it's augmented, so I know there's an invisible ... right there on that last column. This one reads x1 equals 3, 2x2 is 0. Well, if 2x2 is 0, then x2 must have to be 0. So the solution set is 3, 0. And the next one reads x1 equals 3 and 0 equals 2. So that's an example of this bad thing happening. All zeros and then a non-zero number in the answer column. So solution set here is the empty set. All right, and then slightly more interesting, for what values of h is the system with this augmented matrix consistent, meaning it has a solution? So this is my augmented column on the right. I'm going to do one row operation. I'm going to replace row 2 with negative twice row 1 plus row 2. So I'm replacing row 2. The notation is replace row 2 with negative row 1 plus row 2. And as we go through the course, when you do your row reductions, I'll leave it up to you whether or not you want to write down what you're doing over each squiggly line. So I'm leaving row 1 alone, and I'm replacing row 2 with negative 2 row 1 plus row 2. So I multiply 1 by -2, add it to 2 to get 0, And then the next line is going to be 8 minus 2h. And then in the last column, multiplied by negative 2, that's going to be 10. 10 plus 6 is 16. Okay. For what values of h is the augmented matrix below consistent? We don't have to worry about the top row because that has a 1 here, so I'll never get a 0, 0, 0 equals negative 5. That can't happen. But on the second row, I could have a 0, 0 equals 16. If h is 4, then I'll have 0, 0 equals 16. So what I need for consistency is h not to be 4. We're going to do some more of those in the next section. All right, and that's the end.